All right, so let's talk about the, what do we call this lab? Oh, fine gravity or something like that? What is it? Yeah, that's what we'll call it. The lab with the thing and it's going around and, okay. So determine gravity, right? Obviously, your whole point, whole perspective is that you're supposed to use that equation, which you like, whatever, this is the rubber stopper, V squared over the hanging mass times R. This equation was supposed to get you something close, like approximately like around 10 meters per second squared. That's the idea. Yeah, if you're 7, 8, 10, 12, something like that, then you should be able to explain away the reasons why you got it. If you're 20 or 2, then there's something wrong with your data. So you need to like look at your data and figure out, you must find out what the error is. Because if someone's at 7 or 11, then they can say, all right, well, we had about a 20% uncertainty. So that means that it is reasonable that we would get a number that is, that, or it's only slightly worse than our uncertainty. So whatever. But if you got like an order of magnitude off, or if you were like below like 7 and above, for sure above like 12 or 13, then something really went wrong in your calculations, and you have to figure out what that was, right, in order to get credit. Because if you can't explain it, then what did you do? It's like the whole project was for nothing, or the thing was for nothing. So make sure you spend time. And obviously, if you have trouble with that, then you can come see me, etc. Remember that you're going to need an uncertainty, right? We're going to need a total uncertainty, and the things that you calculated here involve velocity and the radius you just measured, right? Now, when we talk about the velocity, obviously the velocity is going to be 2 pi r, right, over, 2 pi r over time. I think that's, well, okay, and then you probably did n, right? N being some number of rotations. Do you remember this? Right, so then if you do that, you get mr times something like 4 pi squared r squared n squared over t squared, and that's over mh times r. So one of those r's can go away, and basically you're just plugging all this stuff in to get this. So the things that you measured, in terms of what are the uncertainties? There are uncertainties in the time that you measured. There's uncertainty in the radius that you measured. Is there any uncertainty in the number of rotations that it went around? Yes, no?
Maybe yes, but like.
Yeah, see, yeah, there is going to be some uncertainty in that as well. It depends on how you did it. If you took a video, then you could reduce that uncertainty to almost 0. Because you could say, well, I can tell within like, whatever, pi over 10 radians. I can set a very small angle, the difference. But, okay, so with this, your uncertainty, you have to find the uncertainty for each of these. Let me see, anyway. Okay, so then you're going to have an uncertainty for the radius, and that's going to be your average radius value divided by the delta r. When I say delta r, do you know what that means? Yeah, it's like you were looking at the bottom of your tube and some indicator, like a knot or a piece of tape. You saw how much it went up and down, yes? So you should be able to say, okay, you know what, I think it didn't go up and down more than like, say, a centimeter, right? If your purse swinger was really bad or spinner was really bad, you could say, okay, it went up, up and down like 2 or 3 centimeters. What, up and down 2 or 3 centimeters, whatever. That lets you determine. That lets you get delta r. Then you have delta t. Okay, now in that one, that's going to be almost nothing because your timer, human reaction time or something, so maybe like 0.2 seconds over your average time. And the times were huge, right? Some people went for like periods of 6, 7, some people went for like 30 seconds or something, or 20 seconds, so 15 seconds, so that's fine. That'll be very small. And then your uncertainty for the number is going to be how far off do you think your guessing for the number of rotations would be? I hope no one here would miss an entire rotation. I'm guessing, at most, people are going to be off by maybe I'm maybe like pi over 3 maybe, because like as it's swinging by, you're saying stop or start, or you're counting it within like maybe a 60-degree arc. I'm just guessing. If you feel like your judgment was worse, fine, make it pi over 2, whatever. And then this is going to be over the full thing. So the full thing is the number of rotations, right? So that's going to be like, and pi over 3 is in radians. So this will be like n 2 pi. Does that make sense? You could also do this. Let's say you said 60 degrees, or even you could say 60 degrees is 1/6 of a rotation, and then you could say 10 rotations on the bottom. It doesn't matter what notation you use; it's all going to come out to be the same. Okay. Now, and then once you have that, because over here we have a square term on n and we have a square term on t, so we have to put a coefficient. So when you finally do the total uncertainty, and you do this, you can have the uncertainty of r squared plus 2 times the uncertainty of n squared plus 2 times the uncertainty of t squared. Because those terms are squared in the term you use to calculate. And if you used omega, then your mileage will vary, right? Because you have to do something slightly different. All right, so this isn't a formula, this is a model. Wesley. What we're doing is trying to say, it's kind of like, pretend like each one of these is like an arrow that you shot at a target. You were shooting for this, and these arrows landed there. Like that's R, that's N, and then that's T, right? And then N and T, because it was squared, there were 2 N arrows, and there were 2 T arrows. So you're squaring the effect of the 2 N's and the 2 T's, or you're doubling the effect of that, but with the 2. And it's because when you analyze the impact, you're using exponentials, so it becomes a 2. But it's just this thing is the average distance from all those things. So like if I look at those 5 points, what's the average distance from the center of this target?
So that's the uncertainty of all uncertainty?
Yeah.
Oh.
So it's like this distance, that distance, and those distances, and it's like the average of all of them. Yeah.
My note says at once, so should I just go?
Yeah, sure, whatever. Yeah. Oh, the number of turns.
Oh, okay.
Yeah. Okay. Any questions on that part of it? So the calculation of it, and that's fine. So what am I expecting? Once again, we look at the multiple things. Okay, and this, of course, is your abstract, and the purpose of this one's pretty clear, was to find gravity by using some weird apparatus. Then here is your quantitative, actually, sorry, let me not put data, quantitative analysis. So there, I want to see all of the stuff, right? The quantitative analysis, we need your SD for everybody. We need your G bar, or average gravity. We need your, take that average and get your percent error. Yeah, percent error. Oh, yeah, and then we need your total uncertainty. So that's what I need to see in quantitative. Nice little table, just shows me that stuff. All those calculations should be in your log or on your Excel page. Yeah.
What's the S?
Oh, standard deviation.
Can you remind me how you do that?
Yeah, I'm gonna show you. It's in Excel. It's super easy.
Oh wait, is it the formula thing?
Yeah, equals STDEV.
I got it.
Yeah, okay, cool. Very good, very good. Yes.
Isn't that the sign means standard deviation?
Yeah, well, that's what, if you're in AP stats, that's standard deviation.
Yes.
But over here, that's uncertainty, so. And then that's standard deviation. It's weird, I don't know why. There's only so many letters, we all have to share, so we just have to get along, I guess. And this isn't better, so I'm not trying to say that, science knows what it's doing and stats, no, obviously. I don't know why it's that way. I mean, hey, you're ahead of the game. When I went to college, I did not even know what standard deviation was. So I saw it in my first lab book in chem, and I was like, what is that? And then the explanation of how to do it, there was no way in Excel, there was no way in a calculator, so I had to do it by hand for every data point. And that is a giant pain in the rear, so just be thankful. Yes?
So we do an Excel sheet for the trials that we did.
A what? Yes. Oh, I'm getting there. Okay, so then finally, this is qualitative down here. And this is where you gotta talk, you have to use, some of you, man, I think I'm gonna not count your lab if you don't start using this correctly. I don't know, maybe I'm too lenient or I just get too sick of reading, but you must use your quantitative numbers here. Okay, and then you must be able to explain the interrelationship between the quantitative numbers. Such as, our value of G was X. X has a percent error of some value from the actual number, right? That number is either, that percent of difference is either greater or less than your uncertainty. If it's less than your uncertainty, then you can say, therefore, I believe that we did a reasonably good job, right? You can then talk about, but we did have sources of error. I believe those sources of error were this, this, and this. And if I could do it over, or if I had to do it again, I would try to do these things to work on that, right? You can also use standard deviation to say that our process was very consistent. So even if this sucked and all of this sucked, right? For example, this, let's say your value was 40%, let's say 60% off of the actual value, but your uncertainty indicates that your uncertainty was like a 0.2 or something, or 0.3, so our uncertainty should have been 20 or 30%, but we were beyond that. Okay, now you have to start doing some very specific talking to me and isolate where things went wrong. If you went up here and you see your standard deviation is actually pretty low, so like your standard deviation is less, let's say it's, I don't know, just for example, say it's less than 10% of your value, right? That means your curve is pretty like this. Like all of your data is pretty close together. That means you can say, all right, our value sucks, but we did a good job of being consistent in our experimentation. So that means something was wrong in our process. Do you get what I'm saying there? Yeah, there's something, and this is what was wrong, right? So you go back, you look at the math, and you let the math guide you to where you messed up. And then we say, okay, here's what it was. We were calculating this with this number, we should have been calculating it with this number, or we measured this incorrectly, that caused this big error. If we did it again, we would fix that. Does that kind of make sense? Everybody get where I'm going there? Yeah.
So standard deviation is basically how accurate your thing is?
No, it is how precise your experiment was. Right? So you remember the thing, right? Like if there's a target like this, and one person does this, and then there's a target over here, and one person does this. Which one of those two is more accurate?
Second one.
The first one.
First one.
Which one is more precise? The second one. Do you remember this?
Keep forgetting.
Yeah. So precision means you do the same thing every time. Accuracy means you're close to the real value. Yeah. Yeah, go ahead. Okay, now, so the second part is obviously Excel. You have a buttload of data, right? Because you have like 5 or 6 times from every person in your group. So I want to see you using Excel. Remember, when you use Excel, and then I think the way I'm going to grade these is just, it's going to be all or nothing. So if you're missing, if one of these things, I'm just going to give it a 0 and pass it back. And then if you remember, you can fix it and then come beg me to regrade it or something. Okay, so on Excel, I need to see the equations. It's not that hard, right? Just copy it, delete the equal sign, and it's going to be there so I can see what you did. Yeah, you're just going to calculate G from there. You can find your standard deviation. You can find your average. You can find your percent error. Probably the only one you need to do by hand is uncertainty. This should take care, for Excel, you should be able to take care of most of your data in one quick shot. Right? The purpose of Excel, even though you may think now is to be a pain in your butt, the purpose is to make life easier. Okay, so that you're not hand punching all these calculations into your calculator. Questions on that?
Do you want all of our data points or just the hat?
Oh no, I want all of your data points. But you only have 15 per group, right? Yeah, 15, something like that. So it should just be all 15 numbers and then average, SD, boom, really quick.
It wouldn't matter if we just had like 10. What it was 60 rotations.
What's that?
If we had 10 trials, what it was 60.
Did you only have 2 people, is that why?
Oh no, because we only had 5. We had 3 people, but we wanted to keep things.
How did you do 10 trials with 3 people?
No, because in week, some of us couldn't do it. That's why.
Oh, it is what it is. Put down what you got, and we'll see how it goes. Okay, questions? All right, yeah?
Policy is part of the error analysis, right?
Yeah, both of these two are error analysis.
Okay.
I mean, this is publication of your results and the beginning of error analysis because you're posting this. I mean, I used to have it separate and all this, but now I'm just trying to make it as fast as possible. And then, of course, this is just the log. Yes?
For n squared in the, try to find the gravity formula, is it supposed to be in rotation? I mean,
Yeah, that's like the number of rotations. And it doesn't matter what you use as long as you're consistent. So if you use radians on top, you have to use radians on bottom. If you use rotations on top, you have to use rotations on bottom. Do you get what I'm saying? If you say, oh, I think I'm off by half a rotation, then you use half over however many rotations you used. Oh, that has to be radians, yeah. That has to be radians. Okay, questions? Any other questions? Yeah.
Do you want standard deviation with gravity or?
Yeah. Just standard deviation of the gravity. Yeah, I'm recording all this. Okay, any other questions? Oh, yes, no, yes.
Well, when you type it onto Excel, you can just easily find out standard deviation. What's the symbol to do it?
Oh, the command?
Yeah, command.
Equals STDEV, open parens, select your thing, hit enter. Right? Average is equals average. And then you can find your percent error very easily by taking your average, whichever one's going to make it negative. I don't want to, you could do absolute value, but that's kind of a pain. So just take your average minus 9.8 and then divide by 9.8, and that'll give you, and then turn it into a percentage, make it a positive percentage, and I'll give you your percent error. I'll write that down just to be clear. Percent error. Obviously, usually you want to use your absolute value, so you can use O minus A over A times 100%. What does that mean for you? Basically, that's your G bar minus 9.81 over 9.81 times 100%. And then there is a command, I think it's like equals ABS or something, but I'm not sure exactly, to be honest. You'd have to look that up in Excel. Or just when you subtract, if your average is less than gravity, then do 9.8 minus g. If your average is bigger than gravity, do your average minus 9.8, whatever. Okay, questions? Anyone else? All right.